Okay, hello. Welcome back. For you, it may have been an hour or more. For me, it's only been a couple of minutes. So it's great to see you again since a few minutes ago. Here's our first lecture on OpenGL. I'm really excited to kind of get into the nitty gritty of this stuff. And then I will also be the final portion of content for this week will involve going through how to set up kind of a general environment in OpenGL and getting kind of things set up. So let's dive in, huh? So OpenGL largely stands for the Open Graphics Library. It's a cross-platform API that effectively abstracts the mucky, junky details of a piece of hardware for the 2D and 3D rendering of that piece of hardware. So back in the day, everybody had their own standards and everything was a mess, and nobody could speak the same language, and so the graphics library, the graphics libraries were used to sort of, okay, I'm going to write one line of code and it's going to go to all these different GPUs and frameworks or whatever, and it's all going to look mostly the same. And we'll talk a little bit about the history of OpenGL and how that came about to exist today. But generally speaking, it does really a few things. It provides cross-platform support and access to the GPU, and it also manages the memory and the pipeline. And so this is actually kind of an important point. Some of the new libraries do not do the second part. They no longer manage your memory and no longer manage your pipeline. So Vulkan and DirectX 12, for example, no longer do this. So OpenGL is a really good way to kind of get up and running with the lower level graphics stuff because some of the new techniques are not batteries included. So OpenGL is like batteries included, although it doesn't do everything for you. I also will want to add OpenGL does support the legacy support of fixed pipeline. We'll talk a little bit about what that means, but I really don't recommend you ever use that. And it's largely there to support old games or old content that was, built a long time ago and has not been updated to the new modern designs. So a little bit about history of OpenGL, and this is kind of an incomplete history, but in the 1980s, like I was saying, people just sort of wrote their own stuff. Back in like the DOS days, it was what's called mode 13H, and you would put DOS into 13H mode, and then you could access the graphics buffer directly. And it was not really consistent across different hardware architectures. Not all CPUs were the same. Not all of the whatever. It was a mess. So there wasn't really a standard outside of a few limited libraries like Borland Owl and stuff like that. As we got into the 1990s, SGI, which is actually down the street from here, really became this leader in 3D graphics, hardware. So they actually built their own hardware and their own graphics cards. Little known fact, right? A lot of NVIDIA actually spawned out of SGI, so you can kind of see the modern manifestation of a lot of that stuff. And they, so SGI built both the hardware and the software, and for that they developed their own kind of proprietary standard called Iris, Iris GL, Iris Graphics Library. They had to. There was no thing out there, as we were mentioning, and it wasn't proprietary because they wanted it to be. It was proprietary because it had to be. As kind of we got into the mid 1990s, and SGI started to lose a little bit of foothold to some of the more modern, like graphics card, like custom graphics cards, and NVIDIA actually spawned out around this time too. As they started to kind of open this up a little bit, and they provided licenses for Iris, and eventually it turned into OpenGL to allow it to work on any. So it be kind of stumbled into becoming a standard, which is pretty cool. So in 1992, OpenGL 1.0 was released, and they set up the Architectural Review Board, ARB, which we'll find throughout the OpenGL code all the time, and to kind of maintain and expand the standard. And so when you see extensions and expansions of OpenGL, you'll often see ARB attached to it. And around kind of speeding up around 2006, the ARB voted to transfer OpenGL to the Kronos group. This is sort of we'll talk about the Kronos group. They're like a nonprofit organization made up by a constituent of many, many companies. Um, and just kind of to speed up to today, the recent version of OpenGL is 4.6, released back in 2017. And there are different extensions to allow for new hardware features that don't break compatibilities with the standards. And when new GPUs come out, they'll support specific versions of the OpenGL standard based on supporting certain extensions of the standard. So that's kind of a little bit about kind of the history of OpenGL. To talk a little bit about the Cronus Group, it's now in charge of the OpenGL API, amongst other standards like OpenCV and OpenXR, and also, I don't know, Vulkan even. So it's a non-for-profit consortium of companies. The promoter companies include AMD, Apple, Intel. It's kind of like a board of directors. These are the guys that put a lot of money behind the development of this API and have a lot of vested interest in the API as it directly impacts the hardware that they're putting out. A lot of other members in this consortium, like EA, Valve, Unity. There's even individual members and contributors in the Cronus Group that are not affiliated with any company as well. OpenGL is used in most places. Actually, it's supported on Windows, OS X, Linux. We also have what's called OpenGL for Embedded, or OpenGL ES, or GLES for short. So you'll find it on iOS, on Android, on Blackberries, even on the Raspberry Pi. A lot of consoles use it, and even in the web. So there's a thing called WebGL, which is effectively a set of JavaScript APIs that allow you to manipulate an underlying canvas element or a context with a lot less. So you can do a lot of the stuff that we're talking about actually in this class entirely in the browser. And you'll be surprised at how effective that is. Actually, I recommend, if you want to mess around with it, go check out like THREE.js, and you'll find that there's some really cool demos on their webpage. It's a JavaScript API for WebGL. So why do we need it? So for the computer to render non-text to the screen, you need to effectively, we'll talk about this much deeper in the future, but you need to kind of create a pixel buffer of some kind. And most computers, started off on text-based, and so the movement into actual graphics was a bit of a stumble because of the limited memory that early computers had. Right, if you have a 40 by 80 console of letters, that's much less memory than, say, a 640 by 480 array of pixels that could be, that have, RGB values associated with each one. So if you look at early graphics computers like the Commodore and examples on the Apple II and stuff like that, you'll actually see that a lot of the graphics are really just a console thing with like blocks that are of particular colors. And there's a lot of really hacky, fun tricks that they used in the early days to make things like the Nintendo worked using palettes and atlases and things like that. So we do need a new way, a better way to draw to the screen than just using text and just using sort of sprites and kind of set pieces of memory. And so OpenGL allows us to draw simple graphics primitives to the screen, both for 2D and 3D applications. And this is a great way for us to really learn and understand the lower level way to access the graphics capabilities of a computer. So really how to access the GPU, in some cases, other things. So this is a really, OpenGL is a pretty terrific API. Let me talk a little bit about alternatives, just so that we're not going to be really working with any of these, but I'll talk about that a little bit at the end. So DirectX, currently on version 12, it runs on all of the Microsoft platforms, so kind of think about it as a proprietary OpenGL. So it doesn't run on Linux, it doesn't run on Mac, it does run on the Xbox, and so DirectX and OpenGL tend to stick pretty neck and neck in terms of functionality and capabilities. Also now DirectX 12, which is a lot more similar to Vulkan. So there's a lot of changes now in terms of how these APIs are looking. It's like, so a lot of these batteries included APIs are kind of going away as more and more people are using things like Unity and Unreal. So nobody really cares about the lower level stuff, which is something I'm hoping to not let happen with this class. But Vulkan is a really exciting API that it kind of takes all the memory management and all the state management and all that stuff that OpenGL does for you, and the DirectX 11 and below does for you, and gives you almost a direct access to the hardware. So if you can kind of imagine on a CPU, on the CPU side, if I want a chunk of memory, I use malloc or new. Vulkan lets you do stuff like that, whereas OpenGL doesn't really let you directly manipulate the memory on the GPU. It lets you through architecture and sort of mechanisms. And so Vulkan's a more direct thing. We'll talk about it probably more often in this class, but it's even more lower level than OpenGL. So not a great way to get started. Metal is sort of the Apple version of DirectX, although you can still use OpenGL on both Mac and Microsoft and all these things. So right now, OpenGL is the best bang for your buck, so to speak. You build it once, it'll work relatively, it'll be compatible, I should say, across all platforms. But Metal is also pretty great API and particularly helpful when you're on iOS, since it's a bit more efficient than OpenGL, given that it's Apple's proprietary direct to hardware kind of thing. So, what can we use OpenGL for? And I'll use OGL because it takes up less characters and I'm lazy. So generally speaking, we can draw simple things like points, lines, triangles, even quads, even other things. We'll talk about those. But like, what about the complicated shapes that we see here? What about a teapot? How do we draw a teapot? Well, nothing cannot be represented by one of those primitives, right? So a teapot can be made up of triangles, made up of quads. We'll eventually talk about surfaces and curves and how those convert, those parametric surfaces can be converted into these geometric primitives. But generally speaking, the way that we deal with OpenGL in this course will not allow us to deal with like pure mathematical concepts like as in ray tracing or what's called signed distance functions. But we'll see if we have time at the end and we can talk a little bit about how you would do something like that with OpenGL. But generally speaking, OpenGL is really good for what's called rasterization. And the rasterization being the conversion of a primitive, such as a line, to a set of pixels on the screen. And that's what we're going to really dive into with this class. What else can OpenGL do for us? We can do a lot of stuff. We can what's called do texture sampling. And so this is the ability to take a texture and then map it onto a quad or onto a triangle in 3D space. We can have different kinds of textures. So OpenGL supports cube maps, which is effectively imagine 6 textures that fit a cube. Also, obviously, 2D textures are the standard, but also 3D volumetric textures, which are used in some really interesting applications. We can also render very complicated 3D geometry. We can render things to textures, which then we can then apply throughout the scene to create shadows, to do reflection, even using deferred rendering to accomplish bloom effects, which are fun. OpenGL supports programmable shaders. So we talked a little bit about the fixed function pipeline earlier, and we'll talk about that again. But effectively, you can imagine that the shader is like an application that runs on the GPU, first on each primitive that you provide, and then on each pixel of the buffer or the screen. This gets really, really deep, and it looks like IGM309 is a class that you can take if you're particularly interested on the more advanced graphics stuff. So we should also know what OpenGL does not do. OpenGL does not open a window. It does not handle the input for you. It does not load textures from the file system or anything from the file system, which you'll find that you'll need to load a few things from the file system. It does not provide with any kind of game loop. In fact, it doesn't provide you with any kind of constructs related to games or to even an engine or any kind of application stuff at all. It's not an engine. And so it's just really strictly a way for you to access the GPU in a safe, compliant way across multiple pieces of hardware. And so everything else is up to you. So OpenGL is batteries included, but let's say it's not the car. You still need to go and get a chassis and all that stuff. So how do we handle all that other stuff? Well, we could build it all ourselves, which we'll do a little bit of. But there's a lot of libraries that simplify using OpenGL, and we'll use a number of them. We'll even work on a little bit of a custom engine, or not. We'll see. More on this next time. The OpenGL API. It's an API. What API stands for is an Application Programming Interface. Like I was saying, it really lets you communicate directly with the GPU of your computer. The GPU explicitly is a chip that sits on your actual, like your video card. Much like a CPU, it manages memory and runs applications, but the architecture of a GPU is inherently parallel in a way where it can run that application on millions sometimes of locations of memory simultaneously. This is a little bit different than like the CPU extensions, that like vector CPU extensions. We're talking about being able to run an application on a buffer of data. So like say I have a image buffer that is 50 by 50 and it's all red, and I want to turn all of that to green. I can do that with one instruction versus having to do that with many iterations. Like even with a vector architecture on a CPU, it's not quite sufficient to run it on 50 by 50. And the GPU also provides a lot of kind of capabilities to scale that up and down. And some of the new modern GPUs really have gotten rid of a lot of limitations that older GPUs had about the size of those buffers. And so you can do some really cool things now without having to worry too much about making sure your buffer is the correct size and that kind of stuff. I will say one thing about GPUs while we're talking about the hardware. In hardware, everything's about efficiency and alignment. So even though you can do something, if you can do something that isn't designed for the hardware, it means that a piece of software or some microcode somewhere is doing something to make that compatible with the existing hardware. So just because you can do something doesn't mean you should. And you'll find in many places throughout this class, we'll be doing funky things like, for example, an XYZ, that's a 3D point, but you'll find that I like to push 4 floats into the GPU instead of 3 because of alignment. And alignment speeds things up quite significantly because things line up correctly, and the GPU doesn't have to convert a buffer into the buffer that the hardware expects or split it up into multiple pieces and chunks and whatever. And so this is both a combination of what OpenGL does for you and also what the hardware does for you. But anytime you do something that you don't know about, that's just bad, like it's less performance. And so you might not see it so much in this class, but when you're doing something really aggressive, you'll find that that's really important to keep in mind. So OpenGL has lots of functions, over 500. They keep getting added as well. There's a lot of stuff that gets added by way of the extension framework, which we'll talk about a little bit more later. But generally speaking, yeah, it keeps the state for you. You have a lot of functions. You can create textures. You can create objects, and you can manage them. And it kind of maintains a state machine to make sure that you don't do the wrong thing at the wrong time. Although I guarantee you will break that state machine more than once, as I have many times. So let's draw some stuff with OpenGL, but like what kind of stuff? So we talked about points, talked about lines, talked about triangles. Triangles is probably what we'll use the most. Most meshes and most models and most objects in 3D are constituted of triangles. They are the simplest thing, right? If you try to make something with quads, it's pretty difficult to do, and lines and points don't take up any space. So triangles is what we got left. And it's a pretty good way to approximate any arbitrary geometry. So using just triangles and just lines, we will be able to recreate pretty much any complex shape to some degree of approximation. So how do we define this geometry? So a point is a single point. a vertex. Um, the definition of a vertex is going to change as we talk through it a little bit more over the next few slides and also through the course. But just imagine a vertex as a point in space, be it in 2D space, in 3D space. You can even have vertices in 4D and whatever arbitrary, you know, whatever arbitrary space you are in. A line is just a set of two vertices and kind of the connection of the two. And then a triangle is a set of three vertices that are all connected. And as you can see, this is kind of important with the triangle. While mathematically a set of 3 points is a triangle, the order of the vertices is important, as you'll find out very quickly, as in which one, and based on OpenGL and the API that you're using. So keep that in mind, but we'll talk about that more when it becomes really important. So a vertex, like as I was mentioning, is just a position, and this breaks down into effectively two. For a 2D point, it's two values, x and y. For 3D, it's x, y, and z. We'll often use a w as well, and this is largely to do with how to do transformations, but also with regards to the alignment of the underlying GPU. Sometimes it's better to utilize a 4D thing, and the W can be used for a number of different things, but we'll talk about that later. So for the next few lectures, we're probably going to be sticking to X, Y, and Z, but if you see the W popping up in the code examples, as I'm working on them, you'll see why. Often, even with 2D points, I would just represent them as 4D, because imagine a transformation applied to a 2D point and a 3D point, even though if you imagine a 3D point and you take away the z, you've just taken x, y and projected it down to a plane. And so there's no, you can try to treat them the same way, but you probably want to know which one's 2D and which one's 3D. So vertices also are not limited to that data, as I was mentioning before. Vertices can have colors. They can have the texture coordinates, or what's called the UV coordinates. They can also have surface normals, so which direction they're going. So in a continuous mesh, you have a bunch of triangles, and that's kind of a rough approximation of a surface. But the vertices themselves can have normals that then represent a continuous surface that those normals are interpolated. So you actually carry that information in the vertex itself. So the way that we define it, a vertex is basically an array of numbers, and that array somehow has to get into the GPU. The type that we're going to use is float, and this is kind of an important thing. I remember, I'll tell a little bit of a story. I implemented one time a little simple 3D engine that ran on an 8-bit 16 megahertz processor that was connected to like a VGA. This is like a 18 mega 32 for you guys that care about that. And I was able to run it at about 15 to 20 frames per second with up to I think 4 triangles. Wow, that was like the max, and it was really impressive. But the first time I ran it, I had a little pyramid that was rotating in space, and quickly the pyramid started like this, and very quickly started to get smaller and smaller, and eventually like disappeared. I was like, what the hell just happened? And this is it's important to know that you really need to appreciate that numbers in computers are not perfect. This is what's called precision. And so a floating point number of 32-bit precision versus a floating point number of 64-bit precision, aka a double, the double will have significantly more precision. And what that means is that as you do multiplications and you do transformations, that lack of precision will affect maybe not that calculation, but games are running at 30, 60 frames per second. You're doing, how many thousands or millions of these calculations per frame. Things add up. And so what I was doing wrong in that particular case was I was using the previous value and transforming that previous value versus using a kind of core, imagine a width and a height, and then using that and then transforming it to get the final value versus rotating it and then rotating it again. So if you take a value and you rotate it enough times, eventually you're going to get to 0. So what you have to do is you have to kind of create a new version of that value each time. So precision is a big deal. However, the higher precision, the bigger the numbers, the more compute you need, and the less performance you may get. So it's a trade-off. You'll even find in some cases things are done at a significantly lower precision than you may ever imagine, but the output is fine. Like if you've ever played a video game and you've seen these really cool reflections and stuff, and the reflection map actually is like 100 by 100 resolution, even though you're playing like a 4K game and you can't tell the difference because that reflection is so warped onto like a bubble that you could never tell the difference. So keep this in mind. Precision is one of the best ways, both in terms of the value precision, but also in terms of how you write algorithms and how resolution and all that stuff. These are like the levers you have, the first and easiest levers to pull with regards to performance. Cool. So now we have some vertices, and what do? Well, we got to get this data to OpenGL. And how do we do that? Well, we're going to use the OpenGL API. Ideally, we want to get this to the GPU only one time. Now, older systems and older fixed function pipelines didn't do this because the GPU was significantly memory limited. And so you couldn't put a lot of stuff onto the GPU, and you would basically feed your vertices every single frame, which sucks. So we don't want to do that. But ideally, but now with with buffer objects on the GPU side, you can actually create a mesh, load it up in CPU, load it onto your GPU, and then you can tell the GPU, okay, now I'm using this buffer, and we'll talk about how to do that. So to kind of more explicitly say why this is it's more performant to do it on the GPU side. Like we could do it on the CPU. However, the CPU is significantly slower at manipulating buffers, as we were talking about earlier, than the GPU. And so that's actually the main reason is the CPU is significantly slower at doing this stuff and manipulating. So say I wanted to rotate a set of 100 vertices, then it's going to take me a really long time to do that. But also taking that data and then moving it to the GPU takes time too, and that's really a limitation of the bus speed of the GPU and the CPU, and also the contention on that bus with other things on your computer. So if we can avoid it, great. And also if we can use the best, the fastest method, we should. And so that's kind of what OpenGL is trying to help us do. So yeah, let's kind of we'll talk about how to do that more in the future lecture. So to talk a little bit about the rendering pipeline, and it's the way that things kind of get to the screen. It's a lot like it's almost like an assembly line. So I personally don't love the name pipeline, but it kind of is like a pipe where you put some stuff in this side and then it kind of comes out and it works. But if you open the pipe up, it looks a little bit more like a assembly line that we'll kind of dig into in a minute. But what's really unique about modern pipelines is that they're programmable. So you actually get to run applications at each stage of that pipeline. So each stage of that assembly line, you get to kind of say, okay, here are the vertices, here's what we do to them, here's how we render them, here's what we do, here's the and then here's how we render the buffer. And we'll dig into each one of those stages pretty soon. I mentioned the fixed function pipeline earlier, and the fixed function pipeline was particularly popular in the early stages of external or peripheral or graphics like hardware accelerated graphics cards. What you could do back then with hardware is you could design a lot of these algorithms in hardware, and then you could just say, okay, here's where you put in the vertices, here's where you put in the color, here's what you can provide, and then it would output the stuff on the other side. But the issue with that is the early things only showed turned a polygon into a thing, but they didn't provide normal mapping, and they didn't provide this technique. And as we found out actually later, as we moved on with graphics programming, sometimes you're doing pretty different things even in one frame, and sometimes you're changing things. And as actually one of the things that I've worked on in the last engine I wrote, that engine was completely dynamic. So when you rendered a frame, it was completely different than each and every frame. And so the fixed function pipeline got us pretty far, but it was limited. It was very unflexible, and so it was really good, but it didn't give people the needs. Like it didn't let us do what we wanted to do. And so the more modern GPUs now have these programmable pipelines that you can basically write these programs that run at every stage. They're much more flexible, much more powerful as well. And that's today's standard. And so everything above Core 3.1 and OpenGL, and basically since DirectX 10, but even DirectX 9, DirectX 10 was kind of this weird transition one. They don't really exist. Although, like I mentioned, OpenGL will support legacy fixed function pipelines, but it actually just does this by way of emulation, so that you don't need to worry about it. So talking a little bit about the rendering pipeline, this is an overview. I do recommend that you guys go and kind of check this out at a deeper level if you want. But this is kind of a high level overview. The only two required shader stages that need to be defined by the application, the API user, is the vertex and the fragment shader, also known as the pixel shader. And so the way it works is you take your vertex input and it gets pulled into the vertex stage or the vertex shader. This is where you applied your projections, your transformations. So you can kind of imagine on the other side of the vertex shader, you effectively have all of your vertices kind of projected down onto a 2D plane, so to speak. And between that, there's a couple of other ones. These are kind of relatively new, but also optional. This is the tessellation stage. The tessellation stage allows you to take, say, a low polygon count mesh and sort of tessellate it so you can have more. If this, like, say, I have very limited and sparse points, I can kind of turn it into more points. I can kind of determine what those points in between are. There's also the geometry shader, which is a really cool shader stage that allows you to generate custom geometry. And what's unique about that is, imagine if you played Zelda Breath of the Wild, or if you played games with a lot of grass, you can imagine that the need for the CPU to tell the GPU exactly where every single blade of grass is and how to change it and all this stuff is really difficult. Like, you can obviously upload it to the GPU and save it as a model, but then how do you manipulate each one of those independently? So the geometry shader, one of the more notable techniques it's been used for is real-time grass, where I can create a field of grass and then I can walk through it and all of the things are bending in response to me being in there. Or, for example, another really good application of it is snow. So say I have a game and I'm walking through a snow field and I want the snow to kind of impact every time I take a step. It sinks into the ground, and so the geometry shade is really good for stuff like that. Okay, those two are optional. So on the other side of those, you have effectively a bunch of points on a flat thing, and that goes into these kind of hidden stages that are the kind of the primitive setup, the clipping, and the rasterization. And what these do is these kind of turn those set of points into an interpolated set of pixels and values that then the fragment shader is operating on. So a triangle, this point on the line would turn into a value that then you can use in the fragment shader to then calculate what color should be at that pixel. So a given point on a triangle will have an interpolated normal, it'll have an interpolated color, it'll have an interpolated location. And also you can do some really fancy stuff here where you can say, okay, these two vertices have this depth, and you can interpolate a lot of stuff. And so the fragment shader is particularly powerful and is a big reason. And once this became a standard, you started to see some really much more photorealistic rendering in a raster pipeline, as compared to a ray trace pipeline or things like that are currently nowhere near real time, although are starting to make a lot of headway as well. So yeah, there's a lot in here, and you probably teach an entire class just on this stuff. So we don't need to worry too much about it today. All you really have to focus on is the vertex shader and the fragment shader. So why is this better? Like, why not just use C++? Like, why do we need OpenGL? Like, why do we need the CPU? Again, GPUs are like just designed for this stuff. It's so much better. We can exploit parallelism. We can process a lot of data. Yeah, this is going to be. I'm going to post this lecture, and you can watch this. But this is a video. This really kind of going crazy about how amazing GPUs are. But there's a lot of really amazing examples of this already. And this is a little bit dated now, but you can really see the difference between what a CPU can do in terms of just pure floating point operations per second, which is how you tend to measure this stuff, and what a GPU can do. And one of the more advanced GPUs out on the market at the time, although today's Titan is probably significantly better than this. In fact, today it's not uncommon to find GPUs up in the tens of teraflops, and you can also you can link them and get even more. So you might ask, actually, like reading this slide, like why don't we just use GPUs for everything? Like why do we need a CPU? Well, GPUs are limited in the way they function. They are really good at dealing with lots and lots of stuff. They're not so good at dealing with like sequential things. So most of the stuff that you do on a computer, like check your email and go on a web page and whatever, is an event-driven thing, and GPUs are really, really bad at that kind of stuff. They're very good at processing lots and lots of data, which is effectively what a computer game is. You're just generating tons and tons of data and running it through this pipeline that is then producing this parallelized thing. So the right tool for the right job. So where do we start? We need to initialize OpenGL. We need to determine which version our computer supports. We need to kind of create the window that we can then render into in the context, the rendering context that is then used by that window. And then we need to create kind of a loop, like a loop that basically runs until stuff happens inside of that loop. Eventually, we'll start to handle input. We'll load shaders from disk, and we'll start to draw real and interesting things. So to initialize the OpenGL it's a lot of code. I know people say it's not a simple process. However, it's boilerplate. So one thing that you'll see in a lot of people like write this stuff and whatever, but it's boilerplate. Like you don't really need to know what all the parameters mean unless you need to know, right? It's like one of those like, if you need to know, then you know. If you don't, then you don't need to care. And I wouldn't worry too much about memorizing the OpenGL API. In fact, most engines, as soon as you write the engine, you wrap OpenGL into this wrapper and you never touch it again. And as you add new features and new functions, you just add those OpenGL things. And so just keep in mind, knowing the OpenGL API is not that important. Knowing what it can do and knowing how it works and knowing how to use it, that's very important. But actually knowing all the nitty-gritty details, it's not that valuable. But it is not a simple process just to get OpenGL up and running, as we'll see in the next lecture, which I'll go through kind of setting it up and getting a window up. Opening a window is not a super simple process, largely because it's a OS-dependent thing. And connecting it to OpenGL is also kind of a very specific thing to the platform that you're on. There are frameworks, there are toolkits that are there to use for this, but initially we'll kind of do it ourselves, and eventually we'll use other things that in some cases also provide a game loop for rendering and give you hooks to do things wherever. So let's talk a little bit about some of those libraries. So one of the more notable ones, Glut, the OpenGL Utility Toolkit. This is really great for small OpenGL programs. It's cross-platform. It just kind of makes everything a lot easier to learn and getting off the ground. It handles the window creation, the management, even gives you input and provides you with a game loop. In the case of getting a little thing off the ground, this is particularly useful. I will say this is coming from somebody who never uses any of these frameworks for any production projects. The benefits of using a framework are really great at first. So if you're doing a small project, like a 2-week project, like do it. However, very quickly you run into things that the toolkit or the framework doesn't do. And so then you're like, wait, like, do I have to rewrite the whole thing? So sometimes you do, and sometimes you have to make an extension or you have to kludge it on. So if you're, maybe not specific to this class, but if you're ever working on a big engine or a big project that you think is going to take you years and whatever, it's sometimes better not to use these toolkits for the graphics library. Sometimes it's just better to like just deal with it, bite down and get through it. But for a lot of the projects that we're going to use these frameworks. So it's a little bit better. So Glut is not in development anymore. I mean, you can still use it, though it's pretty good. But Free Glut is something that is open source and can still be used. The Glue, the OpenGL extension wrangler. This is coming from somebody who's built their own extension thing. Like, extensions are really easy, but they're really annoying. There's like a lot of them, and so using something like Glue, if you don't care about supporting really specific extensions, or if you don't really care about really like deep down configuration of your OpenGL setup and whatever, Glue literally just hits a server and sees a list of like the API list and then uses that to create your local thing. So it doesn't. It's actually just like downloading a web page and figuring out what to do. And if it doesn't find it, it doesn't load it. So that's the thing about Glue. It's the way that the extension setup in OpenGL works is that it only kind of hooks into things that exist. If they don't exist, then it's not a big deal. Great. So a little note on helper libraries. These are not part of OpenGL. Other people have written them to make our lives easier, to make things better. They let us kind of get to the meat of the project, of the problem, but you don't have to use them. So don't feel like you have to. Also, when you do use an external library, there is some setup code and setup steps in Visual Studio. You may have to copy folders. You may have to install things. You sometimes even have to build things. You have to copy DLLs. You have to change properties. Blah. There's a lot of stuff. Managing external dependencies in C++ is not a solved problem. There are ways. We're going to be using Visual Studio largely for this class. Visual Studio just lets you do everything. You don't have to set up whatever. If you want to do things more hands-on, I'll talk about that in just a minute. Feel free to, but you won't have the support that you would otherwise get if you were not to do that. So this is the end of the lecture, and after this I'm going to demonstrate how to create an empty project and getting that off the ground, and getting effectively an OpenGL window up and running, and then also and all that stuff. So next we'll be showing how to get that together, how to get a project up and running, and then also how to get OpenGL showing us a little bit of visual on the screen. And you'll find actually that this next bit is probably the hardest to understand when it comes to OpenGL, because once you kind of understand how to plot pixels on the screen and how to run code on the GPU, from there the focus is much more on well, what do I do in the GPU? How do I get that data to the GPU? And you start to kind of notice that OpenGL sort of fades into the background. You start to really only care about it for sort of specific features and capabilities, like running to a texture and some things that are harder to generalize. So great. Thank you all. Hopefully this was a good lecture for everyone. Please, again, comment on the Discord if you have any feedback or thoughts, or if you want me to change anything, add anything. I know I go on a few tangents and I talk a little bit about my experience with this stuff in the production world. So please feel free to for whatever you want. All right, cool. I'm gonna stop recording. See you next time.